Have you ever wondered why an artificial intelligence model makes the decisions it does? Welcome to the world of black box AI. This term may sound mysterious, even ominous, but it simply refers to a common predicament in AI. Often we find ourselves in the dark about how these models reach their conclusions. They process vast amounts of data, find patterns, make predictions, but the how of it all remains shrouded in a metaphorical black box. Understanding this mechanism is not just a matter of satisfying our curiosity. It carries significant implications for fairness, accountability, and trust in AI. After all, if we can't understand why an AI model made a certain decision, how can we rely on it or ensure it's not perpetuating biases? So let's lift the lid off this black box. Let's dive into the techniques and methods used to make these AI models more interpretable and explainable. Why should we care about explainable AI? Why not let the machines do their magic, you may wonder? Well, the answer is simple. We live in a world where AI influences many aspects of our lives, from healthcare to finance to legal matters. In healthcare, doctors need to understand an AI's diagnosis to trust its recommendations and ultimately make life-saving decisions. In finance, investors need to comprehend how an AI suggests investment strategies to mitigate risks. And in legal matters, judges and juries need to grasp how an AI forensic tool arrived at its conclusions to ensure justice is served. Without explainable AI, we're handing over critical decisions to a black box, risking accountability, trust, and reliability. We need AI models that don't just give us answers, but also explain how they reach those answers, in a way we can understand and validate. Now let's explore how we can peel back the layers of the AI black box. One way to address the black box problem is through interpretable models. Now you might be wondering, what exactly are these interpretable models? Simply put, these are types of algorithms that are easier to understand and explain. They provide clear, understandable rules for how they make decisions, hence making them more transparent and less of a black box. Let's dive in a bit deeper. A classic example of an interpretable model is the decision tree. Picture a tree with branches extending out in different directions. Each branch represents a choice, a decision to be made. At every junction, the tree splits based on a certain condition, guiding you down a path until you reach a leaf, the final decision. This tree-like model is simple to visualize, making it easier to understand how the model arrives at a certain conclusion. Another example of an interpretable model is linear regression, a staple of statistics. In this model, the relationship between the input variables and the output is represented as a straight-line equation. The coefficients of this equation tell you exactly how much change in the output is caused by a unit change in the input variables. This simplicity and predictability make linear regression a go-to model when interpretability is a priority. But as you might have guessed, it's not all sunshine and rainbows. These models, while easily explainable, often face limitations when it comes to dealing with complex data. They might not be able to capture intricate patterns or nuances in the data, leading to less accurate predictions. So, while they shine in their transparency and simplicity, they might fall short when it comes to achieving the highest predictive performance. That's where the trade-off lies. Do we sacrifice accuracy for interpretability, or is there a way to have both? Interpretable models can be a powerful tool, but what if we want more complex models to be explainable? Well, that's a question for our next segment. Stay tuned. Enter post hoc interpretability, a technique that allows us to understand complex models after they've made their predictions. To break it down, post hoc interpretability is a method of explaining the decisions of artificial intelligence models after the fact, hence the term post hoc. This means that we first let our AI model make its predictions, then we apply these interpretability techniques to understand how it arrived at its decisions. Now you're probably wondering, how does this work? Great question. There are several methods used in post hoc interpretability, but today we'll focus on two popular ones, LIME and SHAP. LIME, or Local Interpretable Model Agnostic Explanations, is a technique that explains the predictions of any classifier in a way that humans can understand. Essentially, LIME creates a simpler model that approximates the behavior of the original model around the prediction. It then uses this simpler model to explain how the original model made its decision. On the other hand, we have SHAP, or Shapley Additive Explanations. SHAP assigns each feature an importance value for a particular prediction. It's based on the concept of cooperative game theory, where the players are the features used by the model. The SHAP value is the average marginal contribution of a feature across all possible combinations of features. So, why is this important? Well, imagine you've built a complex AI model that's predicting something critical, say, cancer diagnosis. It's not enough to know whether the model predicts a positive or negative outcome, you'd also want to know why it made that prediction. This is where Lime and SHAP come into play. They can help us understand what features are driving the model's decisions, and in turn, increase our trust in the model's predictions. In a nutshell, post hoc interpretability techniques like Lime and SHAP provide a way to peek inside the black box and gain insights into the decision-making process of AI models. So even with complex models that have layers upon layers of calculations, we're not left in the dark. Post hoc interpretability techniques can help us understand even the most complex AI models. As AI continues to evolve, the need for explainability only grows. We've taken a journey through the enigma of the AI black box, understanding why it's crucial to make these sophisticated systems more interpretable. We've delved into the heart of interpretable models, exploring techniques that build transparency into their very structure. We've also ventured into the realm of post hoc interpretability, discovering how we can glean insights from AI even after their decisions have been made. The field of explainable AI is teeming with potential. Ongoing research is unearthing new methods to pry open the black box, shedding light on the intricate workings of these complex systems. As we continue to push the boundaries of AI, we're not just striving for power or efficiency, we're striving for understanding, for transparency, for trust. As we continue to unravel the mysteries of the AI black box, we move closer to a future where AI is not just powerful but also transparent and trustworthy.